based on this scatter diagram, which I have blown up here, we want to see if there's a linear relationship between the variables, and there isn't in this case. These first points here look like there's maybe a horizontal line that could go through them all, but then these points have a completely different line that would pass through them, and for all the data together, there's not a clear pattern, a clear line that the points lie around. So there is no linear relationship shown in this scatter diagram. So you would choose the data points do not have a linear relationship because they do not lie mainly in a straight line, and then that also answers the second part. Number 2 here, basically the same type of question. I've again blown up the scatter diagram, and you can see all of these points lie along a similar line that would be slanted upward here. And so the data points have a linear relationship because they lie mainly in a straight line, and then it's a positive association because a line would have a positive slope if you drew a line that goes along that trend of the data points. For number 3, we have a table of data here, and this is what correlation is all about, trying to look at two different variables and see if they're correlated, what kind of relationship exists between them. And here we're trying to see if we can use height to predict head circumference. So if we could look at a child's height and from that have a good estimation of what their head circumference would be. So based on the data we have, it says we're going to choose height to predict head circumference, which means the explanatory variable is height, and we're predicting head circumference. So the response variable is head circumference. And then the scatter diagram we want would be right here. And you can tell that just because we want our explanatory variable to be height, so it should be along the x-axis, so that narrows it down to these choices. And our response variable should be on the y-axis, the head circumference. And then look at, this is the graph that has the proper units for height, because our heights range between 25 and 28, and our head circumferences range between 16.9 and 17.6. So height should be on the x, and it goes from 25 to 28 from our table. So D is the correct scatter diagram. You could also draw a scatter diagram in Excel or StatCrunch, or just by hand plot these points, and you would see it would look like that. For C, we're going to compute the linear correlation coefficient, and we'll use StatCrunch to do that. So open it in StatCrunch. We're going to look at go to the Stat tab. We're doing regression, and we're trying to find simple linear regression here. We're trying to find that line that best fits our data. So our x variable is height, and that's used to predict our y variable of head circumference. And hitting compute will tell you what the correlation coefficient is. It's 0.952 because the problem asked us to round to 3 decimals. So 0.952, and type that in there. And then for part D, look at your table of critical values. And notice there were 8 children. There are 8 rows in the table. So when your data is of size 8, we want our correlation coefficient to be bigger than 0.707. And if it is, then we'll say the linear relationship seems to exist. So 0.707 was our target, and we had 0.952, which is larger. So there does appear to be a linear relationship, and it's a positive one. We can tell that because R is positive, but also just looking at your scatter diagram, the trend line that goes through all that data would be sloped up. It would have a positive slope. So B is the correct answer. And if you jump back into StatCrunch really quick, you could see the scatter diagram drawn in StatCrunch if you click the next button here. And there's that trend line, and like I just mentioned, it has that positive slope. So there's a positive linear relationship. And now number 4, we're looking at black bears and trying to see if we can use the length of the bear to predict the weight, which would be useful because it's not very practical to try to weigh a bear out in the wild. It's a lot easier to measure the length of a bear than to get him on a scale. So if we can use the length to predict the weight, that means the length of the bear is going to be the explanatory variable. And then what's that scatter diagram going to look like? You could graph the data here, and you'd see that it looks like D. We're going to use StatCrunch to do that. So stat, we're doing regression, simple linear, and we want the length to predict the weight. And then hit compute. And when you click next, you get that scatter diagram. And length should be on the bottom, the x-axis, and weight's the y. And then just looking back at our choices here, that throws out B because length needs to be on the x-axis. So we have three choices. A's thrown out because you saw from our graph that our line sloping up, the data looks to be sloping positive and upward, and A sloping down. So we really have two choices left, either C or D. And if you look at D, you'll see that D has the same scatter diagram as our StatCrunch. So D would be the right choice. You see this cluster of 3 shows up, the cluster of 2, all the points. It's a little different scale, so it doesn't look 100% identical, but the way the points are dispersed in relation to one another is similar. So D reflects our scatter diagram that we got from StatCrunch. And if we go back then, the linear correlation coefficient. So jump back into StatCrunch, you hit the back button, you'll see it's 0.686. Again, round to 3 decimals. And then for part D, trying to sum everything up, is there a relationship between weight and length of a black bear? Is it a positive? Is it a negative relationship? You use your correlation coefficient. This is a positive number, so the correlation coefficient is positive. Its absolute value is 0.686. And we want to know, is that bigger, greater, or less than the critical value for a data set of size 12? We had 12 black bears. And so if our correlation coefficient was anything bigger than 0.576, we'd say yes, a linear relationship exists. And this is 0.686 is bigger than 0.576, so we would finish saying it's greater than the critical value. So a positive, again, positive linear relationship exists between the weight of the bear and its length. And number 5 here, this is a good problem to help you visualize what the correlation coefficient is telling you. So for A, if R is equal to -1, -1 means perfectly linear correlation. So that would be part, or diagram C here. And the negative tells you the slope is downward, is negative. If R was a +1, it'd be perfectly in a line but sloped upwards instead of negative. And then the farther we get away from 1 and the closer we get to 0, we lose the linearity, and the points are just kind of scattered everywhere. So B is pretty far away from 1 and really close to 0. So B would go with 2 here, where there's not much linear correlation. And then C is actually pretty close to the -1. So you can definitely see where that line would go through the data, and it's sloped downward again because it's negative. But the farther you get away from 1, 1's perfect. When you're close to 1, you still look pretty linear. But then as you get close to 0, the points are more spread out all over the place, and it's not really clear where the best fit line should go. And for number 6 here, we're asked to think about outside temperature and the number of people wearing coats. And there's definitely correlation here. The temperature is going to have a strong effect on how many people wear coats. And will they move in a positive direction together, or will it be negative? And they're going to move in the opposite direction, so that's a negative correlation. And so think about that. As the outside temperature goes up, the number of people wearing coats goes down. So they're moving in different directions. That's a negative correlation. For number 7 here, we have another data set. Start with drawing the scatter diagram. A is the correct answer, and you could pull it up in StatCrunch or draw one on your own on some graph paper, and you would see that A looks exactly like the scatter diagram you get. And then compute the correlation coefficient by hand, but definitely use StatCrunch or Excel to check your work. You should get -0.215. And then once again, and sum everything up and see, because the correlation coefficient is negative and the absolute value of this, it's not greater than our critical value, which we had 5 things in our data set. There were 5 different x and y combinations. So our critical value is 0.878. And because we're not above 0.878, our correlation's way below that, we're going to say there's no linear relationship between x and y. And again, looking back at StatCrunch, you can kind of see that this is the line, the best fit line we could possibly draw, and the points aren't all like clustered around that line. There's some points that are way far away. It's close to a couple, but these lines or these points are in a circle more than on a line, so there's no linear correlation between x and y. And for number 8, again, open the data in StatCrunch. And we're gonna, once again, go to Stat Regression, Simple Linear. Our x variable is x, and our y variable is y. So hit Compute. And you can look at the scatter diagram to help you make the correct choice. The linear correlation coefficient from StatCrunch, go back to that, you'll see it is 0.063. So type that in. And then for part B, we're supposed to add more data and see how that affects our scatter diagram, how it affects our linear correlation coefficient. So we're going to add 10.4 and 9.3. So let's add 10.4 for an x value associated with 9.3. And again, let's do our same steps. So simple linear regression, x and y, and compute. And so now our correlation coefficient is 0.871. 0.871. And so our correlation coefficient is now much closer to the value of 1, which means the data appears to be more linearly correlated to each other than we had previously. This value is much closer to 1 than this value. So the additional data point strengthens the appearance of a linear association. And you can see that from these values we're getting closer to 1, but you could have also looked at your comparative charts here in StatCrunch, and this line seems to fit the data much better than our previous line did when we only had 4 points. And the last part, correlation should always be reported with a scatter diagram so that you can see if the correlation coefficient is being affected by the presence of outliers. So what an outlier will do is maybe there's a very, very strong relationship between the two variables. And you can usually tell that by looking at the correlation coefficient. But if there's outliers, just a few points that are way far off of that best fit line, they're going to make the correlation coefficient much lower. But if you have that scatter diagram, you can visually see that, hey, the x and y variables really are related, and almost all the data fits in a perfect line. It's just those few outliers that are really bringing down the correlation coefficient. So it's good to have that visual picture so you can identify if there are outliers that may be affecting how well the data says the x and y are related.